Hello, physics students. So we just finished the topic, the force of gravity. And what I want to do before we move into the next topic in this video is to remind you of what I said at the start of the force of gravity topic. I'd said that for the first half of the year of this course, we were studying models of motion. What force does? It makes acceleration. It makes energy conserved. It makes momentum conserved. It creates circular motion. But we never really looked into precise detail of what exactly a force is. But then at the start of the last topic, the force of gravity, I said that we would go into what exactly what force was. And so I said that there were only 4 forces in all of nature. One of them was the force of gravity. And that you know very well now at this point that it's like, for example, the earth pulling you down, and when you fall, that's force of gravity. But also that the force of gravity is a mysterious force that creates an attraction between any 2 masses without them even touching each other. So I can jump up. I don't need to be tethered to the earth and I still feel the gravity. But I also feel gravity, or I can't feel it, but there is gravity between me and someone standing next to me. We're not even touching. So it's an attraction between any 2 masses. But in the case, as I said, for everything but you and the object you're standing on, it's so small, you never even feel it. So in the topic, the last topic, it was nice. We talked about planets and orbits. But in terms of you, your everyday experience, the things that are happening to you, we really didn't explain all that much except for why you're rooted to the earth. So in this next topic, we're going to start really explaining what the forces are that are acting on you in terms of everyday experience. Because today what we're beginning, is what's part of something called the electromagnetic force, all electrical and magnetic effects. Today we're just going to concentrate on something called the electrostatic force. And you've learned a little bit about this force, that opposites attract and likes repel, and that charges, like one place where there's charge is in an atom with protons and electrons. So you learned this maybe in chemistry class, but I don't think you learned the full extent of how important this electrostatic force is. Because think about this. As you're going about your life, you're feeling forces all the time. Maybe your friend pushes you. Maybe you shake your friend's hand. You feel that. You have that touch. You can pick things up, okay? So where do these touching forces come from? You say, well, I'm touching it, right? But in terms of our 4 forces in nature, here's what's really happening. The outside of my hand is made of electrons because the protons are inside the nucleus of the atom. The outside is the electrons orbiting around. And the same for this marker. When I go like this and I squeeze this marker, I can feel that. And so what's happening are the electrons in the marker are getting close to the electrons in my hand, and they're repelling each other. Likes repel, minus minus. And so the electrons in the marker repel my hand and they indent it. And my nerves feel that. So the touch between the marker and the electrons is likes repel. Okay? That's how come I feel that. Any touching is exactly that when I hit the wall like that. Electron repulsion stops my hand, dents the wall in. Okay? Maybe handshake, I said, but even the clothing on your body rubbing against you, you could feel that. Same thing, touch. The seat under you. Everything that touches you is negative, this force we're going to talk about. So the sense of touch, all of it is this new force. But it's not just of your 5 senses, touch. If you take salt and you sprinkle it on your tongue, you would taste that. Why? What's happening is your saliva is made of water, or has water in it, I should say. And the salt, the sodium chloride, is breaking apart and dissolving into a sodium positive and a chlorine negative. You learn that in chemistry. Those charges interact with your tongue, create a sensation, create a reaction. Your nerves transmit that by the way with electricity, electrons flowing into your brain. You say, salty, I like it, okay? So anything you're tasting is molecules which are charged up, touching your tongue, creating a reaction through this electrical effect. So we have touch, we have taste, and by extension of taste, smell, which is molecules going up into your nose, and you say, French fries or something like that, right? So that's also these charges interacting. Smell, okay? We have hearing, which is atoms air molecules in your ear bumping up against your eardrum and vibrating. That's electron to electron repulsion, okay, causing your eardrum to vibrate. Now you hear. And finally, vision, sight. Sight is, we're going to learn later in the year, well, you know already it's from light, but we're going to learn later in the year, light is vibrating electric and magnetic fields, the electromagnetic force. All 5 of your senses are caused completely by charge forces, electric and magnetic effects. Huge force. And one step further, even your body is a result of these forces. How so? Your body's made of atoms and molecules. What keeps those electrons orbiting? Remember, we learned in circular motion, without a force, the electron will go in a straight line, constant velocity. What makes it accelerate continuously? Opposites attract. Proton in the middle, electron on the outside, creates a centripetal force, and we have an orbit, which means there are now atoms held together, combined together into molecules, which you can eat, which is part of your body. And then chemical reactions is when, like I mentioned, sodium and chloride charges are interacting and exchanging. Now we have chemical reactions and molecules and life. So much of the world is this force that we're going to be studying now. So let's begin. So we have electrostatic force, the simplest manifestation of this force. And the equation we're going to learn is called Coulombs Law. Now, electrostatic means the charges are stationary. They are not accelerating. They're also not moving with a velocity. Then we need more equations to understand those things. So just 2 charges at rest, like maybe proton, electron. So Q1, Q2, we use the symbol Q to represent the charge. Just like mass, we use M, right? That made sense, mass, M. But charge, we use symbol Q. These have 2 different charges, and they're some distance apart, just like in the case of gravity. But here's a new thing. Gravity always attracted. Charges I already mentioned can repel, but they could also attract. Like charges repel, as you learned no doubt in chemistry, and opposite charges attract, plus minus. But the forces are always equal. This could be a zillion units of charge, and this could be like 1/1,000,000th of a unit of charge. And as we studied all year, it doesn't matter if one thing's bigger than the other. One pulls on one, the other one pulls right back with the same number of newtons, Newton's third law. So I drew repulsion here, but we could have equal arrows coming in also. That would be for an attraction. So that's some concepts. I'll create a pause to allow you to copy this down. All right, next we'll move on to the magnitude or the amount of attraction, the equation. So here's the equation. I just realized I forgot my reference table in the other room. So I won't show you. Well, maybe I'll pause and go get it. All right, back again. It is really important that you be able to find all this stuff on the reference table, because that's what's going to be available to you on the Regents. So where is this formula? And this constant is a lowercase k, by the way. 9 times 10 to the 9th, here are the units. Q is the charge in coulombs, R is how far apart these two things are. So this now is no longer on the back page here. What you have to do is find the electricity section, which is what's considered page 4 of the reference table. And if you look right at the top of the electricity section, you see this formula that I just wrote on the board. Fe is KQ1 Q2 divided by R squared. So now the Coulomb's constant, that K in the formula, well, like numbers like capital G that we used in the last topic, gravitation, the gravitational constant, it's also in the reference table, but you got to go front cover. You have to go a little bit further down, and you see right here, the electrostatic constant K is 8.99. I wrote 9. You could put 9 or 8.99. It doesn't matter. You get full credit either way. Also notice all the units are there for you, so don't forget to bring the units along with you into the calculation. Okay, so, all right, so there it is. And now let's try an example problem. Before I do the example problem, I want to tell you also that you're responsible for concepts in this formula. Like, for example, if the force is 4 newtons and then you double one of the charges, what's the new force? You should be able to figure that out. Oh, 8. What happens if it's 4 and then you separate them by twice the distance? I won't go into all that because I hope you have those skills already from previous forces, but if you don't know how to do that, certainly ask me in class in the next class session. The other thing that's I'm not going to show you is the graphs. What happens if I put a force charge graph? What would that look like? Would it be a parabola? Would it be a straight line? Would it be a descending curve? So that information is in the formula. How about force radius? Also, by the way, all those graphs are question number 1 on today's homework. So we'll see if you could figure it out, and if not, then we'll talk about it in class tomorrow. All right, so let's take a look at this one calculation example. That's what I'm going to do next. So we've got this A2, and then look at this. This is the friction coefficient symbol. Micro, mu coulombs charge attracts a -5 NC, nano coulomb charge, with a force of 0.015 newtons. How far apart are the charges? Okay, so before I explain what those symbols mean, go ahead and write them down. Again, this is like the mu friction coefficient value we used earlier in the year, and this is just a lowercase n before the c. So go ahead and copy those down. Okay, so what do those symbols mean? Well, they're a metric prefix. Like if I said a meter, you know what that is, about this long, right? If I said a centimeter, oh, that's now 0.01, 10 to the minus 2 meters. A millimeter, okay, now that's that, 10 to the minus 3 meters. So all those C, M, K for kilometer, they mean something, as do these. They're just another metric prefix. You don't have to memorize them. Reference table again. So we're on the front cover, and if you go to the lower left now, you'll see prefixes for powers of 10. And so I used micro right here, right there, which, as you can see, means 10 to the minus 6th. Whatever it is, a micro is a millionth, 10 to the minus 6th. And then later I used the nano, and you can see nano is right here, defined as 10 to the minus 9th. So if you ever don't know what one of these little symbols means before a unit, just go right to the reference table and replace the micro with 10 to the minus 6, replace the nano with 10 to the minus 9th. All right, so moving on, I always start by writing the formula out, so I did that. I plug in all my data, 0.015 newtons. The Coulomb's constant, I get that from the front cover, or maybe you remember it, but the front cover right here. So you put that in, and then we cannot put 2 coulombs and 5. We have to now, at this point, realize that it's 2 times 10 to the minus 6 because of the little micro there, and 5 times 10 to the minus 9th because of the little nano there, and then r squared. Now, some people might be saying, why Didn't you plug in the minus? If I plugged in the minus, I would get an error, a radical under the a negative sign under the radical. With this formula, I recommend never plugging in pluses or minuses. It only confuses you. Plug in the numbers, positive. The pluses and minuses are to tell you whether they're attracting or repelling. That's all. Okay? The formula is to tell you the newtons. If they're plus plus, the arrows are going to go this way. If they're plus minus, then they go this way. That's it. That's all the minus would tell us. Okay? And that's all we use it for. So at this point, you just have to do a little algebra. I multiplied all these together and I got 9 times 10 minus 5, the 0.015 here, r squared over here. This is always a little tricky for people. A lot of time people make a mistake solving for something in the denominator. First, what I have to do is cross multiply. 0.015 times r squared, and then the 1 down here invisible, right? Multiply that times 9 times 10 minus 5. And then I got what here, and then I divide by 0.015 to get r squared. Square root both sides, 0.077 meters apart. So about 7 centimeters, which is something like that to create that amount of force between those amount of charges. Now, so right away, right, gravity was weak. We're going to see this later. This force is much bigger than gravity. So it's significant. You feel it all the time. That's why you feel it. Another thing I want to point out is something I've mentioned all year. A lot of students like to do this. Oh, okay, 0.08. Whenever a number is less than 1, they round it to one significant figure, and they make a lot of percent error and lose points on labs like that, and possibly the Regents. So don't do that. All right, let me create a pause to allow you to copy the rest of this down. All right, so very exciting for us. Explains so much, so integral to your experiences, so integral to matter, why it exists the way it does, why there's even life. Opposites attract, likes repel, and always the same amount of force, and force given by this. Plug in just the positive numbers and get the number of newtons, and then figure out attract or repel later. So I hope you enjoyed the video. I'll see you in the next video.